So today I'm going to talk about the Google Titans paper, specifically Google Titans Learning to Memorize at Test Time. And this is a paper put out by Google Research on December 31st, 2024. And this particular paper is an enhancement on the Transformers architecture. Specifically, it enhances the attention mechanism very specifically, and it adds two additions to the attention mechanism and changes. Very specifically, it adds a surprise mechanism, which we'll talk about, and then it adds a long-term memory module, which is very important as well. And it implements this long-term memory module in a very unique way that we'll talk about when we get directly into that. Starting off with the abstract of the paper, the abstract is very straightforward. It just basically states that linear attention, as we know, is not efficient, and it's not mathematically, it has mathematical complications within it. It scales linearly, mathematically, which is problematic when you get to bigger and bigger models and bigger contexts. Right now, we can scale this up to about 2 million tokens of context window, right? That's about the highest that we can get. And then even there, we start running into needle in the haystack type problems. And that's what this abstract illustrates within this. And then so within the Titans architecture, they try to overcome this limitation within the Transformers architecture very specifically. And so they target memory within this. And then so within the Transformers architecture, you have short-term memory built in, but you don't have long-term memory built in. And so that's kind of the first place that they tackle within this. And then the first thing that they mention is that where most people go with this kind of long-term memory is adding it to like these hidden states and hidden dimensions, and trying to create long-term memory via like layers. And they mentioned RNNs and different architectures that do this, and utilizing the layers as memory themselves. And then they bring in this concept of a neural memory, essentially in context memory, where we can essentially update the memory in real time. And as the model is computing, like actually performing the test time compute memory, which is what they build all of the breakthroughs around this, right? And so the difference here between neural memory and storing to the layers is very straightforward. Instead of storing to the layers, you store to the parameters. And so you are storing the information within the parameter itself, compressing the memory to the parameter itself. Like just speaking to this neurologically, neurologically, this seems to me to be the most common equivalent to how my brain likely stores memories. I think that it stores memories within the neurons itself, which means that equates for memories being lossy because you're compressing the memory, right? And you're compressing the memory into the neuron. And neurons can store and act as storage devices just like parameters can. And so I think it's the same type of logic within this, just very simplistically. And I think that's why this works. And then so they do some preliminary testing, and then they do a bunch of math, right? So this is the original attention mechanism put out by the Attention is All You Need paper, very eloquent equation. And then they try to make it more efficient. So this equation in and of itself is not mathematically efficient because this is a linear equation that scales linearly. They want it to scale quadratically instead. And then so they essentially change the equation to this equation that we're looking at here, and then we'll dive deeper into this, right? And then so they go further within this and then break down. This is a really good, in this section, if you're interested in like the history of attention mechanisms from a mathematical perspective, this part of the paper gives you everything that you would ever want, right? Like this is a dream to someone looking for that information. And then so this section 3 is then they dive directly into this long-term memory concept. So learning to memorize at test time, right? And then so they create an equation specifically for this, and then they create this surprise mechanism, and then they have surprise, past surprise, and momentary surprise. And then we'll dive deeper into this surprise mechanism and exactly what it's measuring here in a second when we look at the code in a deeper dive. But So within this surprise mechanism, very specifically, you have the surprise mechanism itself, the forgetting mechanism, which is also important, and then the overall memory architecture and the ability to retrieve the memory during test time. And then so this is always a forward pass that the model makes to retrieve the memory during test time. And you can see that this is the equation and how it works here, the illustration of the model utilizing its training memory and being able to parallelize this process, which is very important as well. And then so that's what they dive specifically into here, how to parallelize all of this. So all of some very complex math that you'll need in order to make all of this work very efficiently, which we're seeing here. And then this paper is then diving deep into persistent memory, how to incorporate memory in context. Very specifically, this paper is almost 27 pages, all about memory related to the attention mechanism itself and all of the mathematics that you could ever want surrounding this. It's a very detailed paper. Then they go into experimental setups, and that's essentially the paper overall, right? And then this then benchmarks conclusion, and then their references, and then everything else within the paper, right? So let's dive into the code of this very specifically. So what exactly is going on here? We have essentially two elements within this, right? We have this surprise mechanism and this long-term memory. So let's talk about what this surprise mechanism is and does. Within a data set, you have redundancies or new information that can be obtained. So I'll use a very simplistic training example. You're training the model on addition, right? So it's 2 plus 2. The very first time that the model sees that, it doesn't know that 2 plus 2 equals 4. It's going to be surprised that 2 plus 2 equals 4. And then so it's okay, 2 plus 2 equals 4. The next time that it sees that 2 plus 2 equals 4, it's not going to be surprised by it. So it's not going to move anything, right? It will already predict that 2 plus 2 should equal 4. So it's not going to move the needle there. It's not going to do anything within it. All of a sudden, if it comes across a new piece of data set and a new piece of data that says 2 plus 2 equals 5, it's going to be very surprised by that. And then so that surprise will move the needle. And so that will make impact on the data set. And we very specifically just utilize that differentiation between the prediction and the actual result to train the model very simplistically off of that. The general thinking is that more likely than not, the model will be surprised because of accurate data as opposed to, in this example that I laid out, an inaccurate example, right? But so diving specifically into how that surprise mechanism works. So you instantiate the model with a standard optimizer, and then within the framework within this, it is important to mention within the Titans paper that they do mention also some changes of the optimizer and utilizing ReLU as the optimizer within this. I don't do this within my example here, but I do want to highlight that they do mention some additions, some ReLU additions within that math that we're looking at within that paper there. But then so the surprise mechanism, essentially it works off of a decay mechanism, and then it utilizes gradient descent for the mathematics, and then the implementation is exactly how I laid it out, right? You pass the model and you propagate the prediction over the weights, and then then you back propagate the prediction versus the actual result like you typically would, but then that's what you utilize then to calculate the surprise, the difference between the predicted and the actual result. If it's a large gulf, you have a big surprise there, and then so the model will pay very specific attention to the area where it has that big surprise. It will pay more attention to that, learn quickly to overcome the surprise within that instance. So very cool how that works within that instance, and then tracking it down, right? What you can see within this is when I train a model off of this surprise mechanism, the loss rate goes down to near zero very quickly because it converges essentially like on what it's initially surprised by, right? Like this surprise, and then passing that surprise back over the data set and back propagating it back over the model weights very significantly impacts the performance. And then so on top of the surprise sequence, so it's surprise plus long-term memory, right? And then so long-term memory is the second major feature within this paper. So let's talk about how exactly it computes this long-term memory. And then remember, this long-term memory is being stored in the parameters themselves, not any other mechanism. So it's compressed and then it's compressed and then stored as like weight information, so a number between 0 and 1, and then so it could be like 0.01112345, etc., and then just a bunch of those together, and then that's what the long-term weight ends up being. So essentially you initialize the long-term memory component itself, then you have your feed forward mechanism that's going to compute the weights to essentially update, and this is like you're updating for the memory, right? This is, and then so you need to compute your initial values, and then you need to compute your attention weights that you want to update the memory with. Then you update the memory, you add your new input weighted by its surprise, so you have that surprise mechanism being calculated here, and then all of this math is being incorporated there. For simplistic sake, I use a very simplistic model to integrate the memory module into. So I just have my, this is the Titans module as opposed to the Transformers module in this instance, making the updates and the modifications that they make for the Titans architecture. I initialize the model with the changes. I run it through a simple training loop. This will all be straightforward and generalized with or without Titans or Transformers. And then we see that our loss rate matches our surprise very well, right? Which is a kind of expected within this instance. And then in this particular instance, I am randomizing this loss rate within this code. So like within that training code. So it's expected that this loss rate is randomized because I wanted to see what would happen within that. Like, does it actually match? That's the kind of test that we're performing here, and it's very close. like there's only very few deviations within that, right? And they're very slight. It matches it very well. And then so putting this all together, how exactly does the model update this long-term memory during test time? So this is how it creates a memory in and of itself, right? It creates the memory via surprise. If it's very surprised, it creates and it stores that surprise in its long-term memory. And then so how exactly does that look like? Because the big thing that they mention within this Titans paper is that this updates in real time, like at test time, right? So what's that process look like? And so that process is a little bit different and a little bit more involved. The very first thing that we do is we are defining our Titans architecture again. So we define our long-term memory module, our update for our memory module, and then we need to incorporate that memory into the module, right? Into the model. And then so essentially how it's doing this is via right here, this forward pass. And then so essentially what it does is very specifically, it calculates the surprise and like that function exactly as we talked about, the differentiation between the predicted output and the expected output, and then it passes that as a forward pass over the weights, and then that's what it's essentially to calculate the surprise as a gradient magnitude, and then it updates that gradient magnitude based off of the amount of surprise. And then so that's kind of like the dial that it pulls, and that's how it's able to update its parameters in real time. And then as we can see here, it goes through and then it updates, and this is simulating how it works as far as the loss rate. And I don't know, right? This is only just one test within this, but just highlighting and showcasing within this kind of what happens to me is that you have what is initially kind of like an increasing loss rate a little bit, which is intriguing. And then the loss rate looks like it starts to go down slightly, and then it goes down a lot, and then it just spikes. And then like from that spike, I would think that something's very wrong. But then by step 10, it's it's essentially memorized the results. Like so essentially, like if I looked at this and I cut it off at step 6, I would think that something is very broken within this model. Like something's not right. But by step 10, like I couldn't replicate this amount of perfection with any other model. So it's interesting what happens there within that 4 steps that essentially the model retains and learns the long-term information, which is exactly what you would want, right? That's what you want from this model. That's what's occurring from here. It seems to me that it by loss 10, it is stored this information into its long-term memory. It does its job. It seems that Google Titans, from a code perspective here, is doing exactly what they laid out in the paper. And I've just laid out for you what the paper does and what the paper lays out. So if you like this type of content, please like and subscribe, and I'll leave a link to both the paper and this code notebook in the description.